Get an idea that I was thinking that slipped. I know
No, I think squats and had it on the back like this, and maybe it was slipping and he freaked out trying to catch it. But like bent his wrists back. It's possible.
Definitely do it for separate ways. I don't know how old.
Rename it.
Yeah, I don't know.
I think we would.
We got it. Just kind of, but I really don't want.
Put some booty in a little bit. Yeah, we haven't watched it.
No, I need to watch it.
All right, well, we're going to get started because it is 6 o'clock. So we got some interesting programming concept to talk about today. It is a kind of a continuation of what we talked about last Thursday, but also an extension at the same time because we're going to talk about recursion today. I'm not sure how comfortable you guys are with recursion. Yes, go ahead.
So I noticed when I was writing the code, I was using the postfix notation to do like 3+, but it didn't pile and I didn't put a space in between.
Yeah, you do need a space in between.
Why is that?
That's because I was lazy, and I use a space as a separator of all the components. The parser was written entirely in JavaScript. You can actually read it if you go to the, let's see. So if you go to the assembler and then you go to extensions, go to app script, you can actually read all of the JavaScript that I wrote to support the implementation of the assembler. Originally, I was thinking about doing it entirely using just spreadsheet formulae. That turned out to be not easy, so I had to rely on a little bit of JavaScript to support some of the functions. Anyway, so what we'll do today is we are going to, I probably send more announcements than some of your online classes or some of your professors here with online classes. No? They send more? Okay. But this is a face-to-face class. So technically speaking, the Zoom, the use of Canvas, announcement, those are all kind of optional things. It also depends on whose class we are talking about. I know some people actually, some online professors also do not do a single thing in 3 weeks. And that's an 8-week class. Yep. Anyway, so we are going to talk about the program that I included in this announcement. I don't know whether you guys actually finished reading the entire announcement or not, but I felt it is kind of important to kind of put in the expectation of the program that swaps a routine. If you spend up average, that's kind of the expected amount of time. Now, if you do it in 2 hours, great, okay? But if you do it in 4 hours, you go like, oh man, I'm not even getting close. Keep going. You're in the middle of it, okay? So that means time budgeting is really important at this point of this class. All right, so what we'll do today is we are taking a look at the string compare program first. So this is a string compare program written entirely in C or C++, but it really is just plain C. So we'll go ahead and implement this program today. So the first thing is, are there any questions about this program before we get started? In other words, what I'll do is I'm going to copy and paste this into my local machine, and then we'll use GDB potentially to take a look at what happens when you run this program. So let me zoom in a little bit. Probably one more time. Yep, that's good. All right. And I got this program here already because I wrote it originally on this machine. So string compare.c is already here. So do we have any questions? Okay, let's try to read this line by line. Line 6 is the prototype of string compare. I have to attach a lowercase t because otherwise the linker would actually complain to say that I de-implemented string compare, which is a part of the standard C library. So I have to change the name a little bit just so it doesn't complain. The prototype is not too difficult. PA is a pointer to a construct, and PD is also a pointer to a construct, which means from the compiler's perspective, it just has to be that I'm not overwriting what PA is pointing to or what PD is pointing to. But I can change the parameters themselves. I just cannot change what they point to. Do we have any questions about the concept of a const? And obviously in the swap subroutine, those pointers do not point to const something because the whole idea of the swap subroutine is not to change the parameters, but to change what they point to. So you have to remember the effect of your subroutine is supposed to change what the pointers or what the parameters point to, but not the parameters themselves. All right, so moving on to line 8, 9, and 10. That is one single expression. Yes, it is kind of long, but it is a single expression. It is a nested ternary expression. So I did not add any parentheses around the whole thing. So I'll give you guys two guesses. Okay. Do you think the ternary expression is left associative or is it right associative? In the absence of extra parentheses, how does it group? Like in this case, okay, let me give you the two choices here. So do you think the extra parentheses go around here? Or do you think the extra parentheses go, I don't even know there's another option to do this. I think that might be another one. So I can group it from here. No, I don't think there's another way to do it. Yeah. So the only way to do the parentheses is to do it like this. But that pair of parentheses is not necessary because it is right associated. Are we good so far? Does that make it clear? Like what this subroutine is doing? It's a nested event basically. Yes.
Right associative means it groups everything the way it is.
Right associative means it would, in the absence of extra parentheses, it will group things on the right hand side first. The implicit parentheses are on the right hand side. Okay, so given this is what the code means, what exactly is it doing? Yep.
It's testing to if the first character of PA or PA input is, if those are the same, if they're not the same, then it returns back. It looks like the subtractions or whatever the difference is between the two.
Yep.
And then if they are the same, then it'll go into the secondary piece, which is asking if PA actually contains anything. And if it does, it calls a recursive function of the previous or of the following two letters. So in string, let's say string, they'll go the second character of both of those. So st or t and t. So compare those both. And then it'll continue doing that. Otherwise, if PA does not have anything in it, it'll return back to 0.
That is correct. So string compare, okay, so one thing we might want to do first is to look up, how string compare itself works. So this is in what we call a man page. Man stands for manual in this case. So in the man page, it describes the string compare, compares the two strings S1 and S2. A string is really just an array of characters. The locale is not taking into account blah, 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 the comparison using unsigned characters. String compare returns an integer indicating the result of the comparison as follows. Okay, so there we go, keep going. Oh, okay, just. All right, so go down a little bit. All right, so string compare returns a 0 if the two strings are exactly the same. It returns a negative value if string 1 is quote unquote lexically less than string 2, and a positive value if string 1 is lexically greater than S2. Do we have any questions about what I mean when I said lexically less than versus lexically greater than?
Saying less than equal.
It's basically using the characters or the ASCII code of the characters to determine what is greater than and what is less than. So if the ASCII code of one character is less than the ASCII code of the other character, then it's considered to be less than. Okay, so we do, yeah, go ahead.
I just have a question. If like, let's say string 1 is string and then string B is string alpha or whatever, where
It's
they have
longer.
different, character thing.
Yep.
Just because we're testing on just if string 1 has anything in the following. Would that return back here or would that return back?
It'll return back a string. The first one is less than the second string.
Okay.
Because it will, all the characters would match up to the null terminator of the first string. The null terminator has an ASCII code of 0, which means nothing can be less than that. So that means the second string has to be considered greater than the first string.
Okay.
But in this case, it's better to say the first string is less than the second.
Okay.
Yep. All right. So it looks like we got a pretty good grasp of what string compare is supposed to do. This doesn't tell you how to do it, okay? It just tells you what it does. Do we have any other questions about what string compare does? Did you guys talk about this in 360? Okay. All right, okay. So if you do have any questions, just kind of bring up the questions as we talk about the algorithm. All right. So the recursive algorithm, okay, there are several ways to kind of make this easier to read. This is the then value, and this is the else value. But the else value is its own conditional statement. So this is the condition, this is the then value, and then this is the else value of the nested ternary expression. So this might be a little bit easier to read because now it actually resembles more of an if than else. So once again, line 8 is the if, line 9 is the then, and then line 10 to line 13 would be corresponding to the else of the outer ternary expression, and then the nested ternary expression starting on line 11 has the if on line 11, the then is on line 12, and then the else is on line 13. So it is a nested ternary expression. But we can do this, okay? Is that okay? Do we kind of get a good grasp of what the nested ternary expression, how it works and how it is structured? And of course, I can also make. It doesn't like to. There we go. I'm just changing the nesting of the parentheses so that it makes a little bit more sense like that. All right. So how does it work? Yes.
I'm actually curious. So from what I'm like deciphering, what you're doing when you're calling the function again is you're going on the next character.
Yes.
But you're not doing it in a regular way. You're incrementing the memory address.
Okay, so the question really is surrounding what we call the addition to a pointer or pointer arithmetic in general. So when you add a number, be it positive or negative, to a pointer, it changes the result of the expression is going to be, are we looking at the next thing? Are we looking at the previous thing? Because you can actually subtract 1 if you want to. We seldom do a subtraction, but sometimes we can do that if that is necessary. Does that answer your question?
Yeah. So
okay.
It just goes to the next value, like the next character.
Yeah, it's basically a shorthand. In other words, if I were to comment here, PA plus 1 is really the same thing as the address of PA bracket 0, bracket 1, close paren like that. So these two expressions are exactly the same. PA plus 1 has a pointer plus 1, which means what is the address of the next thing? but I can also express it like this. What is the address of the next element compared to the first element of PA? Because in C and C++, any pointer can be seen as an array. It's a nifty feature sometimes. Most of the time, it's bad because it can lead to a lot of problems. So are we doing okay so far in terms of the expressions in this particular program? Good. All right. So now we're going to implement this program, okay? But before we do that, I'm just going to give you guys a quick explanation. So on line 8, we're basically saying, from the perspective of a string, if the first characters are different between the two strings, do I need to go look any further? No, I got a conclusion right now, okay? So all I need to do in that case, if whatever PA points to is different from whatever PB points to, in other words, if the first characters of the two strings are different, I can make a conclusion already that the two strings are not the same. But in order to return the value, all I need to do is to subtract whatever PB points to from whatever PA points to, because remember, the standard of string compare is really to return a negative if string B in this case is greater than string A, or returns a positive integer if string A is greater than string B, and this subtraction gets the job done. It doesn't say anything about it always has to return +1 or -1. Remember, the man page only says something about the sign of the return value. It doesn't tell you, what is the magnitude of the return value. Is that okay? All right. So what if they're the same? What if PA points to a character points to PB, and whatever PB points to, they're exactly the same character? Well, then we might have some more work to do. So we go to here and we check, okay, PA, are you pointing to a null character? Or I should say, are we pointing to a non-null character? Because if that is the case, it means, okay, we have to look at the rest of the string, because I cannot determine the order between these two strings. They have exactly the same first character. Let's check out the second character, the next character. So instead of using a loop to check out the next character, I just go like, hey, I can look at a string as a character followed by a substring. So PA plus 1 is referring to the substring, everything other than the first character. PB plus 1 is also the substring of string B, because it is everything except for the first character of string B. So this is a very typical strategy to use a recursive algorithm, which is to look at the original problem, break it down to a tiny little piece that I have to do. In this case, it will be the comparison of the first character of the strings. And then if I cannot make a conclusion, then I turn it into a subproblem that has the very same nature as the original problem, just a little bit smaller in this case, because it has one fewer characters in this case. Is that okay? But if PA points to a null character, so is PB. Okay, how can I tell that PA and PB must be both pointing to a null character by the time I get to line 13? Exactly, because if they were different, I would have gone for line 9 already. So by the time I get to line 11, 12, and 13, whatever PA points to have to be exactly the same as whatever PB points to. The only question is it null or non-null? Okay, very good. So now we can go ahead and implement this program. And I'm going to keep it like this, okay, kind of a little bit more spelled out and use more spacing, so it's easier to read. And then, over here, we have some literal string. So we're going to talk about how literal string translates into assembly code as well. All right, so I'll be kind of ready to move on to translating this code into assembly. Yeah. All right, cool. We can actually try this code first, and use GDB and also backtrace just to take a look at it. I think we'll do that. So we'll go ahead and say gcc-g-o string compare.c GDB string compare, and then we'll put a breakpoint on line 8, run the program, And then we do a backtrace like this. Okay, so we are now at the first invocation, main called t-string compare. And that's where we are at this point. But we know the two strings, I think one is tag and the other one is what? Taki, T-A-K-I. Okay, so we know the first three characters are the same. So the first three invocations would not be able to make any conclusion until we get to the fourth invocation. So we continue execution, and then we do another backtrace, and now we have two invocations of t-string compare on the stack. And it's not conclusive yet because your AK and AKI, they both start with the character A, so I cannot determine the order yet. So continue, backtrace again, and now at the top we have K versus KI, which is also inconclusive. So we have to continue one more time, and at this time when we backtrace, we can see there are 4 invocations of t-string compare on the stack. Are we doing okay so far with this? Now, the nice thing about GDB is it will show you and interpret the parameters by default. You don't even have to go for like print, blah, blah, blah. Okay, so it does show you, what we're dealing with here. It also shows you the actual address of the character. Because the first time we call, we are starting with uppercase T, that is at the address ending with a 9. This is ending with an A, ending with a B, and then ending with a C. So you can see how the pointer PA+1 is literally just adding 1 to the address and then pushing on the stack. Let the next invocation deal with it. Yes.
I'm actually curious. I just noticed that we had the other memory address like go immediately before it for TAC.
Yep.
If you look for PB, why is it before it?
That is up to the compiler to decide. The compiler is just saying, okay, we have 2 literal strings and they need some storage somewhere. And the way it allocates is entirely up to the compiler. They can be contiguous, they can be all over the place, but it's up to the compiler to determine that. Yes.
I was gonna ask about next to the 1, 2, and 3. Do you have the same exact memory address for all 3 of those?
Yes. That is where the breakpoint is when the program calls.
Okay.
Yeah. Since this subroutine only has one single breakable statement,
Yeah.
so they all have to be the same.
Okay.
But if you put multiple breakpoints into a more complex subroutine, then it might go to different places by the time it calls its execution. Then you will end up with the different numbers here, and they will not all be ending up with 1 A to B, because that is telling you, when we do the call to the next invocation of t-string compare.
Okay, I thought that those were actually the return. But not.
I think that's the return address. It is the return address. All right. So is this helpful? I mean, do you think if you are to take a class, with recursive algorithms and you have to write a program for that class, I think this is going to be really helpful because you can actually tell what is going on the stack, how many times it's calling itself. And you can even go back to a previous frame and ask, oh, okay, from the perspective of frame number 2, in this case, what are my local variables? The local variables not shown here, only the parameters. But in this case, we only need parameters. There are no local variables. All right, are we doing okay so far? And then if I single step, it's not going to be very exciting because the last invocation is going to return the value, and then that became the return value of the second to the last invocation, which then becomes the return value of the second to the third to the last invocation, and so on. So it would collapse the stack without being able to single step through the whole thing. It might be able to single step through the whole thing. We'll see. So this time it's returning PA minus PB, and then we jump all the way back to line 15 and then line 9 again. So, okay, so it's good. I mean, it does actually, but it's not returning PA minus PB every single time. So this part is incorrect. It did not return to line 9 because it cannot. If you have a single expression that spans across multiple lines, it will report the wrong number because it cannot track which part of the expression you're at when you are going through a single expression. Are we still doing okay so far with the tracing of the C code? Because that would be the first thing to do is to find out, okay, what does the C code do? Because if I don't understand what the C code is doing, there's really no chance that I can write the assembly code and check whether the assembly code is going to do the same thing or not. All right, so by the time we get back to main, which is right here, we can now print out what is X. All we care is that X is negative in this case, which means the string tag TAK is less than the string TAKI, because one has a null terminator, which has an ASCII code of 0. The other one has the ASCII code of I, which has the ASCII code of 105. I can tell right here, and that's how it works. All right, so unless there are questions about this, we'll start the assembly code implementation. Are we good? Okay, all right. So we'll go ahead and I cannot remember. I think it's an uppercase O to split side by side instead of top down. So string compare.ttp ASM. Yep, okay, that's how we do it. All right, so we're going to use the new approach. We have a no op, we initialize the stack pointer, which really is not needed, but I want to emphasize that we do want the stack pointer to start beyond the last location in memory space. Oops. And then we basically call main, okay? We have LDIA with .6 plus, and then we have decrement D, ST, DA, and then JMPI to main. That's basically the call to main. And then when main returns, I have nothing else to do, so that would be a halt instruction here. And then we can implement, do you want me to implement main first, or do you want me to implement string compare first? Main first, okay, so we can do that. So let's go ahead and take a look at main in the C code. It's not too complex. So when we look at main, we do have one local variable. So we want to allocate space for that local variable. So we want to take a look at what is the stack, what does it look like by the time we get to the entry point of main. We have the return address, which is pushed by the unnamed code, which is from line 3 to line 6. That's the call to main. So we do have the return address, already pushed on the stack. We want our local variable X to be here. And then we also want to move the stack pointer so that it points to X here. So that means, X as a local variable of main should have an offset of 0 from where the stack pointer points to once I adjust the stack pointer to allow for local variables. So are we still doing okay so far with the comment of line 10 and line 11, which is really just a crude way of looking at the stack, and also line 12, which is a convenient way for me to refer to the offset to a particular local variable of main, right? All right, so if this doesn't happen right away, because I have to remember to allocate for local variable X with a decrement, and then we do an increment at the end of the subroutine before we do the actual return code. So the actual return code is returning, okay, I probably should put LDIA 0, because we are returning a 0 on line 21. So I'm just replicating that over here. And then we have the typical 3 instruction to return to the caller, which is LD, B, D, increment D, and then JMP, B, like that. So now I can insert the code in between. All right, so the first thing we implement in main is line 20. What do we need to do first on line 20? I cannot do the assignment first, right? Because the assignment relies on the right-hand side giving me a value first, which means I have to call string compare. But in order to call string compare, it expects 2 arguments, and as a result, we have to push the arguments first. So this is where you guys might have a question of, so how do we push strings on the stack? Well, when you talk about string, which is double quoted in C and C++, it is really the address of a bunch of bytes. And that is statically allocated. Every single constant is statically allocated. So what we need here is go somewhere, okay, somewhere between main, after main, it doesn't matter. So now we have to create, two literal strings. So I'm going to use underscore literal string 1 to basically be the label marking the beginning of the literal string tag. And the way we do this is going to be very tedious because we can only declare 1 byte at a time, and the assembler does not understand what is a character. So now I have to look up, what is the ASCII code of uppercase T and so on. So we'll go ahead and do that using a separate tab. All right, so we have to kind of make the terminal a little bit shorter because otherwise I can't see the bottom. There we go. So fortunately, in Linux, the man pages include the ASCII code. So I can just look up the ASCII code of T, which is right here. And in decimal, it is 84. Oops, wrong key to press. So this is going to be 84. This is, that's basically the ASCII code of uppercase T. And then we have the ASCII code of lowercase a. I know that one. It's 97. The way I know this one is because I can remember it is 61 in hexadecimal. 61 in hexadecimal is 6 times 16 plus 1. Yep.
You have to write it in decimal, not hexadecimal.
Yeah, you can only do it in decimal because the parser in TTP ASM, the assembler cannot deal with anything other than base 10. I have yet to add a feature to deal with other bases. If you guys want to contribute code, it's welcome. So this is A, and then K is, oh, okay, wrong key again. So what is lowercase k? Okay, there's lowercase k, which is 107. Oh, I keep keeping wrong, 107. And then the first one has a null terminated here. The second one, okay, this is the first string. And then I would just copy all these bytes because I just need to add a lowercase I between the 107 and a 0. So there are 5 lines here. And there we go. This is literal string 2. I just need to add an I here. And I'm too lazy to get, count with my finger. So I is 105. And so 105 goes here. That would be taki. All right. Do we have any questions about line 9 to line 20? How we declare 2 literal strings in this case? Yes.
So we wouldn't say that these string literals are on stack.
They're not on stack. The address will be on stack by the time we call the subroutine, but the actual arrays are stored, basically look at these as const, but without the name. So the compiler internally would refer to these quote-unquote arrays that are initialized, that are const, but it doesn't have a name. So it cannot just refer to the name of the corresponding to the address. Are we doing okay so far? All right. So now back to main, I can now push the addresses. So to push the address in this case is pretty easy. I just have to LDIA with __ literal string 2 because we pushed the second argument first. Okay, so remember that. That's a caller-callee agreement. You push the last argument first on the stack. Decrement D, STDA. So that pushes the second string, LDIA again, __ literal string 1, decrement D, STDA. That would push the first string on the stack. And then the rest is just the usual way of calling and returning from a subroutine. So we have LDIA .6+, decrement D again, STDA, and that pushed the return address on the stack. So now we can just continue execution in the string compare subroutine. When we get back from the string compare subroutine, we have to clean up the stack first because the 2 arguments are still sitting on the stack. The subroutine will take care of as in popping the return address, but the 2 arguments are still sitting on the stack. So at this point, the two arguments are useless because the subroutine is already done. Why do we want to keep the arguments on the stack? So we increment the stack pointer twice to get rid of the arguments that are still sitting on the stack. Now remember, what is still sitting on the stack are not the content of the string. It's not the characters TAK and then the null character and then TAKI and then the null character. It would be the address of those things that are still sitting on the stack. In this architecture, each address is only 1 byte. So, incrementing the stack pointer twice, we get rid of both of those arguments. But we still have register A containing the result of the subroutine. So we have to stash it into local variable X. So the way we do that, okay, which is, okay, we cannot use A because A still has the return value. So we have to use some register other than A and D in this case. So we load the offset into a register. We add the stack pointer to the offset so that we end up with the address of the local variable. And then we just need a STBA in this case to store that value into the local variable. And that's the end of it. All right, so any questions? So right now, all of these things are things that we have already talked about from last Thursday. So it's more or less, just a reminder of what we have talked about, and it's just a repetition, just so that you guys get exposed to this kind of code again. All right. Are we ready to move on to the string compare subroutine? Okay. All right. Question?
Just want to scroll up so I can copy this.
Well, the whole thing is being recorded right now, so you might want to just jot down the timestamp. That makes it easy to locate it. And I'm going to share the code with you too, so I'll send it as an announcement when it's all done. All right, so now we get to the subroutine, which is string compare. Okay, and let me switch the C code to the corresponding part, like so. And now we can, so for the first thing that I usually do is to kind of get a picture of what is on the stack. So this time, string compare does have parameters, which means those things would be occupying the higher address part of the call frame because those are pushed by the caller prior to pushing the return address. So we'll have PB over here. We'll have PA, oops, over here, and then we have the return address over here. And by the time we get to the entry point of the subroutine, that's what the stack is going to look like. Yes?
Don't we have one more return?
No?
Isn't that from main?
But why do I care? That's not, that is none of my concern. As far as the subroutine string compare is concerned, there could be a whole lot of stuff above the PB, but those are not my stuff. I should not care about that, nor should I mess that up. Because if I mess that up, I'm not only messing up myself, I'm messing up the caller as well. Now you go like, yeah, but that's only happening when you're writing code in assembly. That is not the case. If you write code in C and C++ and you use local arrays, okay, local variables that are arrays, and you index out of bound, you can end up trashing something that does not belong to the subroutine. So the symptom is going to be very strange because the subroutine may even appear to be 100% correct. It gets its job done. Depending on what you trash on top on the stack compared to what the locations that belong to you, you can mess up something from 2, 3, 6, 4 callers away, which means the symptom won't happen. It will not be observable until you are well past the point of where the error happens. So those things can happen. So when you have a mysterious problem happening with your C++ program, you want to look for corruptions like that, which typically happens when you index, when you use an array or overwrite an array out of bound. All right, okay. I know it's hard for you guys to imagine that kind of problem because you have not written a lot of programs that can potentially end up with those issues, but trust me, it will happen. unless you go to SAC state where they use only Java and not C++. Then it won't happen. Yeah.
One of my friends at Sac State, he said that a couple of his professors allow you to use like whatever like language you want, so long as it will compile and do Linux. Like that.
Okay.
So he has fun and goes through a couple different languages and does it that way, and they're like, okay, thanks for turning it in like this, but like, make something more readable, please.
Interesting. In that case, I would choose to use Common Lisp. Just so that I have so many parentheses, the professor would be dazzled by the number of parentheses. Just a whole lot of parentheses. Yes, Lisp. All right. Okay. So the way I do this is I will also give these things names. So I have CMP. The return address is going to be at the offset of 0. And then the next one is going to be PA. So T string compare PA. It's going to be T string compare return address 1 plus. And then PB is going to be PA 1 plus. And now we have symbolic names referring to the items on the stack. So this way I don't have to remember. Okay. I know it is just a matter of counting 0, 1, and 2, but I prefer to use symbolic names if I can. All right. So now we look at the code in C, and then we go like, it looks like we need to get to whatever PA points to, and also whatever PB points to. And I guess it makes sense to put whatever PA points to into register A and whatever PB points to into register B. I mean, you can use any 2 registers you want to between A, B, and C, but I just thought this is easier to remember. Okay, so we'll go ahead and do just that. LDIA with T string compare PA, which is an offset from where the stack pointer points to the local, well, okay, it's a parameter in this case, PA. So it's only until you add the stack pointer to the offset do you end up with an address of the parameter. And since it's just an address of the parameter, we have to dereference it once to get to the parameter itself. And because we don't want to compare the parameter, we want to compare what the parameter is pointing to, we also need to dereference it one more time. Okay, so now at this point, register A would be the same thing as whatever PA is supposed to point to. So PB is going to be about the same thing. So I would just do the lazy but not safe thing. Copy and paste is not exactly safe to use because if you forget to change, if I forget to change one of these lines, then I can end up with a piece of code that seems correct, but it is actually wrong. So, use it carefully, okay? All right, so do we have any questions about line 63 to line 71 at this point? Yep.
I have a question for 59. Is that line necessary?
It's not, it's just that, I still, this way I really know where things are. So you can look at line 59 as quote unquote comment, because that label I'm not going to use anyway, but I do want to kind of make an entry for that. So this way, I know where other things are relative to the return address. So for the purposes of teaching this class, it is useful, but for the purposes of really just referring to the parameters, it is not useful. All right, any other questions before we continue with this program? Okay, all right, so we shall move on then. All right, so now that we have the left-hand side and the right-hand side of the comparison, we'll just go ahead and compare, right? CMP AB, there we go, okay? And we are basically saying if they are not the same, then we can just return whatever A minus B is, okay? I got a better way to do this. Okay, so I'm gonna backtrack here. I know this is not a good thing to do, but I'm gonna, well, okay, maybe not. Okay, I'm not gonna backtrack, never mind. In my mind, I was exploring two separate branches of how to implement this code and see which one is slightly more optimized. But I decided to go with the one that is the easiest to understand, which is what we'll do next. Okay. So after I compare, okay, we have to look at the flags. Remember, we got 5 flags whenever we do a subtraction or an addition. So we are going to affect all 5 flags in this case. So those will be the 0 flag, the carry flag, the sign flag, the overflow flag, and also the L flag. The L flag, carry flag, sign flag, and overflow flag, those are useful if you want to see which one is less than which one. But that's not what we don't care about that, okay? We just want to know, are they the same? So the Z flag is the only one that makes sense to us, okay, that we're going to use. And we don't have a JNZI, which means we cannot say, what if the 0 flag is a 0? There's no way to state that. We can only have a JZI. But in this case, the JZI actually kind of works out because we can then go to the else case of the top level ternary expression. In other words, this would branch to whatever is equivalent to line 11, 12, and 13. So that's basically corresponding to the else of the top level ternary expression. So we'll just label this as else here, okay? And then I just stash a label here just so that I remember where to put it. And then I usually just also comment here to say this is the then case. And in this case, I would also confirm what it means to be here. Whatever PA points to is different from whatever PB points to. That's just my habit, okay? You don't have to do this, but I find this to be helpful because this way, by the time I get to what is currently line 78, which will be later on changed, by the time I get to implement whatever code is on line 78, I would know what it means to be there. Because if I don't do this, I would have forgotten. And we also use a jump around. So we will use a jump around here. So we have a JMPI around the else branch to the end of the ternary expression. So we'll just enter here and ternary expression, and then we'll just stash it here. I forgot one important thing. I forgot to write the return code. So the return code is the usual of LDBD, increment D, JMPB. Because if you do forget the return code, things will be very awkward because it will execute all the no ops after this all the way until the end of round, and it will basically use the stack content as if they are opcode. So who knows what that's going to do, right? It all depends on what is on the stack at the time. So it's really important to remember to put in the return code so that we actually do return. All right, so any questions at this point? And I just have the framework of the outer ternary expression at this point. I have not stuffed what it is supposed to do with the then, also the else branch yet. Yep.
So in this code, you are immediately dereferencing all the way down to the value of PA and PB. But since we access it so many times in all the different branches, would it be more efficient to just leave the locations of PA and PB in A and B, and then load them into C for value? Or I guess if you need to compare two values.
Yeah, exactly. If you need to compare, we only got 3 spare registers because register D is already in the stack pointer. Right. So you're going to have to reload some of the registers anyway. Yeah. And then the most immediate thing we need to do are all based on the dereference of the pointers anyway. So we only need to get back to the pointer themselves by the time we get here.
Gotcha.
Yeah. So it's, I understand what you're talking about, but this is also an interesting discussion because it would seem to me that the more registers that we have, the more optimal we can make the code because we don't have to keep reloading the same thing over and over into the registers. And that is actually true. So newer architectures tend to have more registers because this way the compiler can make much better use of the registers to hold values so that we don't have to recompute values over and over again. All right, so now we can go back to the then branch, and the then branch only got one thing to do. It's okay, let's return the whatever A minus B is, because A already has whatever PA points to, register B has whatever PB points to. So that's pretty easy to do. We just have to do a subtract AB and we're done. Because register A stores the result of register A minus register B, which is exactly what we want. So we can just kind of skip around the else branch, go to enter, and enter continues with the return code of the subroutine. We are good. Is that okay? All right. So now we move on to the else branch of the top level ternary expression. And I'm going to nest everything with extra space here just so that it is visually easier to understand. So now I got a second question to ask, because now I have to ask, is PA pointing to a null character? All right. So based on your experience up to this point, what is the most efficient way to check whether register A is a 0 itself or not? Yep.
We add a because
it pushes register A through the ALU. And whatever you do, so the carry flag, sign flag, overflow, and the L flag, they are only affected by add and subtract. But the Z flag, I take it back, the sign flag is also affected by just about anything that pushes through the ALU. So that means after this instruction, the Z flag and the S flag, the sign flag, will both be affected based on the bit pattern in register A, which is super handy because I don't want to compare to a 0 unnecessarily. I mean, that will work too, but it's not necessary in this case. So I can just do an AND AA and then see if it is 0. And once again, I can only do a JZI because there's no complement to JZI to say jump if the Z flag is a 0. I can only jump if the Z flag is a 1. I just have to adjust the branching pattern accordingly. So according to this code, that works out too. Because if PA is pointing to a non-null character, we want to fall through to this code. If it does point to something that is a null character, then we just go ahead and return whatever, we return 0 in that case. So it does work out, and I am going to shortcut the whole thing and just say, let's just go to enter. We're done. And then someone's going to say, attack, didn't you forget to specify a return value of 0? Because that's what it's supposed to do. The answer is yes, and I have done it already. Why? Because register A is confirmed a 0 by the time I get to enter from JCI. Because that's the whole point of JCI, is to say jump if and only if the Z flag is a 1. Why would I know that A is a 0 already? Because the immediate the instruction immediately before the JCI is just pushing the value of register A through the ALU. Is that okay? So I did a little bit of optimization here with a JCI directly to enter. Are we good so far? All right. So what is left to do now is the recursive call. So I'm just going to say recursive call here. All right. So the recursive call is nothing too surprising, right? I mean, we have to push PD plus 1, then we have to push PA plus 1, then we have to call the subroutine. Sounds pretty simple, okay? But there's one little twist here, okay? So we'll get, when I get to the twist, I'll mention it. Okay, so the first thing we need to do is we have to figure out what is PB again, because even though earlier I figure out what it is already, by the time we are done with line 70, it's lost now, okay? It has been long lost. So we're gonna have to, I mean, I could have saved it here and then reuse it here, but just for clarity, it's not a bad idea to recompute it here. So we look at, we load into register A, the offset to PB, add the stack pointer to the offset. So now we have the address of PB, and then we have the LDAA, so that A register A now is PB. And then we have to increment it so that it becomes PB plus 1. We don't have to store it back, okay? We are just looking at the expression PB plus 1 here. So we have to push register A at this point, which is a decrement D, STDA, and that would have pushed PB plus 1 on the stack. Are we good so far? So you gotta look at this code and go like, oh, okay, so we just have to do the same thing with PA and we are done. But let's check out what's gonna happen here. So we'll copy, okay, so we are copying line 87 to line 93 to here. And we just have to change here this reference to PB to PA. And you go like, well, aren't we done? Well, not quite, okay? This is now problematic because the offset to PA is not right anymore because we just push one extra thing on the stack. Okay, remember PA and PB as labels, they are indicating the offset in number of bytes from where the stack pointer points to at the entry point of the subroutine to the respective items on the stack. But the stack pointer has changed because we just pushed something on the stack right here. So that means the offset is now one more than what we have, the way we define the labels. So that's why we have to actually say, well, not quite. We have to adjust it by adding 1 to it. Yep.
Just say A, we don't have to add it to B.
Just the A, because when we push PB on the stack pointer is still at the same as it was at the entry point of the subroutine. It's only because of line 91 that it is now different. Now, there are several ways to fix this problem, okay? You can also pre-compute the PA plus 1 by not pushing anything first. So you can store PB plus 1 into register A, PA plus 1 into register B, and then push those registers later on. Then you don't have to worry about the adjusting for the offset to the items. But in this case, I want to make sure that you guys understand why we have a 1 plus on line 94. So are we okay so far? I can show you a diagram. I mean, I think a picture would be helpful in this case. So let me switch to the picture. I'll use my trusty stylus. All right, so at the beginning of everything, we got PB. Oh, okay, that's doing ruler mode because of my previous class. So we put tools, turn off draw line, and use this color. Okay. So on the stack, we have PB on the stack, we got PA on the stack, and we got return address on the stack. So the label PA normally is just storing the offset, which is a 1. The label PB is normally just storing the offset to B because register D points to the return address at the entry point of the subroutine. This is the way we computed the offset, and then we use those offset to define the labels. Is that okay? So by the time we are done with line 92, we would have pushed PB plus 1 on the stack, which means in terms of the diagram, we would have PB plus 1 here, and then the stack pointer would now be pointing here. So that means if I need to go back to PA, it is no longer just 1 byte away from where the stack pointer points to. It is now 2 bytes away because we just pushed 1 extra thing on the stack. So you have to account for that extra stuff that you push on the stack by adjusting the label and turning it into an expression. Just add a 1 plus to it, and that fixes the problem. So let me switch right to this code here. So are we good so far? Did the picture help? I hope so. Okay. All right. So now that we got both of those arguments pushed, we can now call the subroutine. And that's a typical thing of LDI A with .6 plus, decrement D, STDA. So that pushed the return address on the stack, and then we have JMPI to string compare, And then when we return, we have to remember to adjust the stack pointer to get rid of the 2 arguments. And that's it. And the result is in register A already, because the call to string compare returns the value in register A. So that means I don't have to do a single thing, because this becomes my own return value. So I don't have to do a single thing. Register A already has what needs to be there by the time the subroutine returns to these 2 lines, lines 107 and 108. Yep.
The 2 increments of D on the bottom, what is that? Deallocating again?
It's deallocating PA plus 1, PB plus 1. It's also deallocating PA plus 1. Because these 2 decrement Ds are not taken care of by the callee. They have to be taken care of by the caller. And then following through to enter is the fine thing to do, because we are really at the end of the entire ternary expression. So we're all done here. Are we doing okay so far? Now, there are several ways to look at this program. What I have just done is to write a code, which is a static description of how to get it done. But looking at the trace will give you a better idea of what is actually being pushed on the stack, what is being popped from the stack. How do we calculate the offset? Okay, I'll give you one example here. So in this particular program, if you want to, you might want to go to the trace and actually see how line 94 to line 99 gets the job done. And then you can actually get to see how the 1+ is actually correct. The way we do this is the correct way to figure out PA plus 1. All right, so are we ready to go? Ready to kind of test run this code? Okay, so instead of using River Spider, I'm going to do this manually. This would be the 3rd time I do this entire thing manually in this class, just so that you guys get another exposure of how to do it manually for those of you who don't want to go through the trouble of using River Spider. All right, so we'll go ahead and stash the program into my clipboard first so I can copy and paste it. So this is something that only I have to do because I'm using Linux. You probably have a different way of doing the same thing. So redirect from, there we go. And then we switch to the browser. There's my browser. There we go. Go to the assembler, go to the source tab. So this may be a good time to kind of jot down the time, because I'm re-demonstrating how to test run this code, but without River Spider. All right. All right, so we check out RAM file. Everything looks good. File download as a CSV, and we want to call this string compare. Okay, string compare.csv. And then I switch back to the command line to run logisim from the command line. So this is going to be a pretty long command line here, but you guys should know how to do this part already, because I started to introduce the concept of running logisim from the command line, I think in week 1. So that's like, what, 12 weeks ago? So in processor, logisim, okay, there we go. So that runs logisim. Then we have to specify to load processor 0004, which in this case is in the same folder. There we go. So if I were to press enter right now, it would just load up the processor in logisim in GUI mode, which is not what I want to do. So now we have to specify a dash load, which means it's going to load the RAM file content into the only RAM component in the circuit. So that would be in the local folder, because it's in the temp folder. I believe it is called string compare.csv. And then we have to specify, do not go into GUI mode. So that's -tty table. And if I were to press the enter key right now, it would dump everything on it that's with standard output, which is not useful to me because that's a lot of zeros and ones for me to track manually. So instead of doing that, I'm going to track everything or redirect it to string compare.tsv, which is a tab separated value file. And then we press the enter key. In case you guys are asking, Tech, do you normally write your command line like this long? The answer is yeah. Fairly common thing that I do, when I need to work on stuff. So press the enter key. Okay, it's all done. So now we switch back to the assembler. We go to trace raw data, and we go to file, import, and then we specify upload, browse, and it is in the temp folder. It's called string compare.tsv right there. And I can double click it. There we go. And then this is the important part. Okay, so make sure that you remember to only replace the current sheet, not the entire spreadsheet. I would specify tab as the separator, and then also uncheck convert text to numbers, dates, and formulas, and then click import data. I know it's a little bit of work, but once you get used to it, it's not too bad. All right, so with this all done, we now switch to the analysis tab right here. And then we can try to find out what is being stored in local variable X of main. Where is it? So the stack was empty to begin with. It has the return address so that main can return to the entry code. So that takes up location 255. 254 is the location immediately below the return address, which is also where we are supposed to allocate for local variable X of main. So now we're looking for the overriding of location FE, and that will give us a clue of whether the program worked correctly or not. So this means I can focus on just column C, because column C reflects the way we overwrite content in RAM. And FE is one of those locations. So we can just specifically look for the overwrite of location FE. So we go to file, we go to edit, and then we find. I normally would use regular expression. You don't have to use regular expression if you don't want to learn how to do that, but I find it to be really useful. So I click that. And in this case, we're looking for the reference of FE getting a content of something. Okay, so this is the, if you really want to be sure this is at the beginning of a cell, you can add a caret too. So the caret symbol basically specifies from the beginning of a cell. So this way, I'm not going to match after FE equals to in the middle of a string, which doesn't happen anyway, according to the output of this code. So I'm just showing you some additional stuff here that you might want to learn in order to use a regular expression. All right, so we find, and it gets 97. You guys go like, Tech, you got it wrong, because in the C code, we got negative 115. Was it 115? I think so. Maybe. Well, something like that, exactly. Yeah. But 97, that's, what is it? 97 is, okay, first of all, remember it's supposed to return a signed number. So 97 is corresponding to 71. So it's a negative value. And the next question is, how negative is it? This is actually quite negative, okay? Because the least negative number is -1, and it is FF. FE is a little bit more negative. FC is even more negative. This one is actually quite negative, okay? It is pretty close, well, okay, it's close to the end of the range of all the negative numbers, okay? So if I need to find out what the negative value really is, what do I do? This is just to check whether you guys still remember the assigned representation. And then we apply two's complement. Very good. Okay, excellent. That is exactly what we're gonna do. So it's F97. So we'll switch to Zerno. So this way I can work on this, kind of using my stylus, if I can find it right there. Okay. So we have 97 as a hexadecimal number. So we have 1001 as the 9, and 0111 as the 7. And we want to apply two's complement to this so that we can find out how negative it is. So this whole thing, if I do something like this, arithmetic negation of the C2 of this thing here, I should end up with whatever is on this side will be the value being represented by this thing. The other way to do this is to use the sigma notation. So we can say we are adding 1, 2, 4, no 8, 116, and also a negative 128. That's the other way to do it, which I think is actually faster. So let's do it the other way because I want to do it in a slightly faster way. So we have 1 plus 2 plus 4, no 8, but we do have a 16, and then we have a negative 128. So that would be what, 23 minus 128, which is negative 115. Or 105. 105. There we go. 105. What is special about that? Well, we look up the ASCII code because it should be negative the ASCII code of I. Okay, so we'll check out. Okay, we'll check this out. We'll check out the man page of the ASCII table. Look for lowercase I and see if that is the case. So lowercase I is right here. This is in octal, this is in base 10, this is in hexadecimal, and we see 105 is indeed the ASCII code of 5. The reason why it is returning negative 105 is because we subtract the ASCII code of I from the ASCII code of the null character, which is 0. 0 minus 105 is negative 105. So the program did the whole thing correctly. In a weird way, I'm kind of disappointed because if the program doesn't work, I actually get to teach you guys how to debug the program. It's not the same if you intentionally break something and then later on say, see, I can now fix this thing because I intentionally broke it to begin with. It's good to have a completely careless and unintentional mistake and later on go like, why is this program not working?
Might have something that
Like someone else changes.
Yeah.
I walk out of the room, you guys come up here and change like 2 lines, right? All right. So are we okay with this program? Are there any questions related to this program? Okay, first of all, I want to make a few points. When I called string compare from within string compare, did I do anything that is special? Because that's a recursive call. Did I break the rules about the caller callee thing because they are exactly the same subroutine? No, it's exactly the same way. Okay, we push the arguments, we push the return address, we continue execution, and when the subroutine returns, we clean up the stack. We have to clean up the optional arguments and use register A as the return value. But that's exactly the same thing we have been talking about, right? So I hope this helps to demystify recursion, because recursion as a mechanism is as boring as any function call, because it really is exactly the same. What is tricky about recursion, okay, let me get back to the C code so I can show you that. So what is tricky about recursion is how we come up with the algorithm to begin with. That can be a little tricky. In this class, you don't have to worry about that because I always give you the C code to begin with. So your job is to convert the C code into assembly code. But that should not make, recursion should not make it any more difficult because it really is the same mechanism. And this is why when I taught CISP310, I introduced the concept of recursion already. Because if someone says, I can deal with normal function call, But recursion, I cannot understand. I don't know how to track it. Even if I was given the code, I don't know what it does. That means that person did not fully understand what it means to be calling a subroutine and what it means to be returning from a subroutine, because it's exactly the same mechanism. All right, any other questions? Any questions related to this program or the one that you're supposed to work on, that's due on Thursday? Okay. Did you guys notice, how many hours I mentioned that, on average, you should allocate time for? 8 hours. Yep.
Doesn't matter how efficient or inefficient it is, it's just if it gets the job done, you follow the rules.
Yep, you have to follow the rules and then get the job done, yes. So it doesn't have to be efficient, don't spend the time to try to optimize the use of the registers, because I know many of you will be tempted to do so. It's like, I just computed that, I could have reused it. Wait, I don't have enough registers to juggle. So don't worry about that. After each statement, just start with a clean slate and just like, okay, we'll just pretend that I did not have anything pre-computed and start over again. Huh? You probably cannot really overcomplicate things, because the way I would approach this is I would just compute the right-hand side and then compute the left-hand side and then do the store. So it's pretty hard to really way overcomplicate. All right, so I know you guys are itching to start tonight's lab. There is a lab tonight. I will give you the access code of tonight's lab. Give me a second here. Huh? Nope, because there's no point in doing so anymore.
Yeah.
We are stuck.
I miss like the roll call.
No, we're kind of stuck at this point. I'm not sure whether it's a good thing or a bad thing. Yeah. So the access code is framed, because all we have talked about so far, those are all framed. Parameters, return address, duration variable.
Could have done Roger.
Oh, I used to have an employee called Roger. Roberts. Yeah.
Call them rabbits.
Yeah, I had to try very hard not to smile on class. Yep.
When you after you feel it, keep going down to the back. So this one is the back and then this is. Like we
So we keep going down. So the first invocation will compare the T, the second invocation will compare the A, the third invocation will compare the K, and then the last invocation will compare the null terminator versus the R.
also down.
Just keep going there.
Okay.
Yeah, if you look at the trace right now, you can actually track how the stack is being used, and then you can actually see how we have 4 invocations altogether.
Make sure you submit the thing.
Or invocation.
Mhm.
All right.
Make sure you submit the thing.
Huh?
Thank you.
Okay, sure.
Make sure it's.
Okay, what did you say?
4 invocations of
No. What? Justin said.
the TTPASM.
Right. Okay, I'll do that when we get to the lab.
Is it
Mhm.
okay if I leave earlier today? Extend the lab for me, please?
Oh, extend the lab?
Yeah,
Okay, is there a reason?
I don't feel good today. I don't think I can extend the lab. So,
Well, since it's the first time you need this, I think I'm okay with that.
thank you. Yeah.
You not sick? Because you were with your family? No.
Are you sick, or are you just tired? Because,
I don't know. I've been sick since last week.
oh, so you were sick, you have been sick. Ah, okay.
Yeah, but.
Okay, so when do you think, how much of an extension do you need?
Business card?
Hmm? I cannot do that, okay, that's a very subjective. Okay, all right. All right, I'll see you guys over there.